First of all, I welcome all the students and the participants who are attending this live lecture. See this, in this today's live lecture we shall discuss the problems based on or examples based on the comparison tests of the integral. That means the integral which are improper. We have discussed, we have studied the comparison tests. Again you have seen useful comparison integral, and by using the useful comparison integral, by using the comparison test first, now we have to solve problems based on this comparison test and improper integrals. We have to prove the some improper integrals may be convergence, and it is possible to prove by using the comparison test. See this. Now students, check this. Actually this is the part of useful comparison integral. Now we shall discuss the see this. These are the notes, important note which we have studied up till in this unit, in this chapter. The improper integral from a to infinity f of x dx is said to be convergence if limit capital X tends to infinity, integral from a to x f dx exists. If this limit exists, then we can say that the given improper integral is convergent unless it is a divergent. We have proved. Second integral from a to b f dx converges by using the comparison theorem. Integral from a to x f dx, which is a less than m, where m is the positive number, m is a positive real number, and if integral from a to x f dx, which is a less than m, and m is the positive real number, then we can say that integral from a to infinity f dx converges as x tends to infinity for all capital X greater than a, means x tends to infinity. Also we have seen the comparison test first. If f and g are positive functions such that f of x is less than or equals to g of x for all x in closed interval a comma x, then integral from a to infinity f dx converges if integral from a to infinity g dx converges. Second, integral from a to infinity g dx converges if integral from a to infinity integral from a to infinity g dx diverges here if integral from a to infinity f dx diverges. See this is very important note here. F of x is less than or equals to g of x. This means that if g of x diverges, g of first condition, g of x converges, then we can say that f of x is also converges. F of x is also converges, because convergent means it has a real value, divergent means it has an infinite value, that is which tends to infinity. Divergence means second part, g dx diverges if f dx diverges. जर f of x dx diverges असेल, integral f of x dx diverges असेल, then we can say that g is also divergent because g is greater than f. मग f ची जर व्हॅल्यू इन्फिनिटी असेल तर g ची व्हॅल्यू डेफिनेटली इन्फिनिटी होते. According to this comparison test first, means it has two possible results. If f of x is less than or equals to g of x, f of x is less than or equals to g of x, in this case if g of x converges, means it has a real value because g of x is greater than 0, then f of x is also converges because f of x is less than g of x. This satisfies the condition first. Similarly, if f of x diverges because f of x is smaller than g of x. F of x diverges means f of x tends to infinity, then its bigger value also tends to infinity. That means these conditions given by the comparison test first. This is actually comparison test first. Now comparison test second. If limit x tends to infinity, f of x divided by g of x is equals to L, where L is the non-zero finite number, then f of x and g of x converges or diverges together. That means suppose f of g of x diverges, then we can say that f of x is also diverges. If g of x is converges, then f of x also converges. That means f and g behaves same condition if the limit x tends to infinity, f of x divided by g of x is equals to L. F of x divided by g of x which is equals to L. See this, students, is it correct? Now this is the case. This is the theorem number 4 is also comparison test second. Now this note number 5 is also comparison test second. It has a special case. If limit x tends to infinity, f of x divided by g of x tends to 0, then in that case L ची जर value 0 होत असेल, then we can write integral from a to infinity g dx converges, and म्हणजे डिनॉमिनेटर जर कॉन्व्हर्जंट होत असेल तर न्यूमरेटर सुद्धा कॉन्व्हर्जंट होतो इफ इट टेंड्स टू 0. म्हणजे लिमिट की जर वैल्यू 0 होत असेल, अगर लिमिट की वैल्यू 0 होती है and g of x integral from a to infinity g dx convergent, then we can say that integral from a to infinity f of x dx also convergent. See this. This is the special case of this limit 4. Note 4 ची ही special case है. This 5 is a special case of note 4. Now note 6 is also special case of note 4. If limit x tends to infinity, f of x divided by g of x tends to infinity, and if g of x denominator, if L tends to infinity म्हणजे L ची व्हॅल्यू जर इन्फिनिटी होत असेल and g of x diverges, denominator divergent होत असेल तर numerator also divergent. That means this implies that integral from a to f infinity f dx also diverges. See this 5 and 6 are note number 5 and note number 6 are the special case of note number 4, that is the comparison test second. Also we have seen one theorem, useful comparison integral. This is a useful comparison integral. आपण एक comparison करण्यासाठी useful theorem आपण पाहिलेला आहे. Integral from a to infinity c upon x raised to n dx or 1 upon x raised to n dx, a greater than 0, converges if and only if n greater than 1. n ची व्हॅल्यू जर greater than 1 असेल तरच कॉन्व्हर्जंट होतं, आणि n ची व्हॅल्यू जर लेस दॅन 1 आला तर डायव्हर्जंट होतं. इफ n is less than 1 then it diverges. We can write also if n less than or equals to 1 then diverges. We have proved this, but we have to use this comparison theorem to show the given improper integrals are convergence. Okay, अशा पद्धतीने हे theorem आहे. Write down all these 7 notes because these are the very important note which is used to solve the problems. See this. Now we shall discuss the problems based on this. आता यातले काही प्रॉब्लेम आपण घेतलेले आहेत स्टुडंट्स. काल 2 प्रॉब्लेम झालेले आहेत. आता आपण नेक्स्ट कंटिन्यू करू, पुढचा प्रॉब्लेम कंटिन्यू करू आणि मग सॉल्व करू. सी दिस. We shall discuss the next problem. Discuss the convergence of, I shall write, examine the convergence of integral, third problem, following See this is the third problem. Now we can write this third problem, integral from 0 to infinity e raised to minus x square dx. 0 to infinity e raised to minus x square dx. Now we have to discuss the convergence of this integral. This is very simple integral. Students, now you tell me at which point this integral goes to infinity. Here in this case the given integral is, okay, I shall write first I is equals to, student write down where, at which point this integral, at which limit, lower limit or upper limit, this integral is becomes improper. Write down in the chat box, integral from 0 to infinity e raised to minus x square dx. Okay, this integral is improper at the right end. Let f of x equals to e raised to minus x square. Okay, if we consider f of x is equals to e raised to minus x square. Now we have to consider another function g of x, which behaves the same like e raised to minus x square. Now suppose that if we consider the g of x, but first of all you compare the terms, you know that you must compare the terms. Okay, now say this f of x is equals to e raised to minus x square. Now 0 is not a point of infinite discontinuity, so we have to here 0 is not a point of infinite discontinuity. So we have to examine convergence. So we have to check convergence at infinity. We have to check convergence at infinity only. Okay, now we have to check the convergence at infinity, means right hand. We know that actually we have the comparison e raised to x square, which is always greater than x square. This is the simple, e raised to x square is always greater than x square, because the value of e is, student, can you tell me what is the value of e? The value of e is nearly approximate equals to 2.718. That is 2.7. So 2.7 raised to x square, which is definitely greater than x square. This is the simple comparison we have to consider here. Now by taking the reciprocal, so 1 upon e raised to x square, which is less than 1 upon x square. If we take the reciprocal, then inequality changes, greater than changes into the less than. So we can write, this implies that e raised to minus x square, which is less than 1 upon x square. So suppose if we consider here, suppose we consider g of x is equals to 1 upon x square. We consider g of x which is equals to 1 upon x square, because we have to use the comparison theorem. This can also we use the comparison theorem. that means by the comparison test first, if f of x is less than g of x. Now we shall discuss the integral of this g of x. Here integral 1 upon g of x dx, which is equals to integral 1 upon x square dx. Now you tell me, you know that according to this theorem 1 upon x raised to n converges if n greater than 1. 1 upon x raised to n, c चा सोडा, c ची काही अडचण नाही, c is a constant, but 1 upon x raised to n, this integral converges. This integral converges if n is greater than 1. Same problems here, integral from, we can say that 1 to infinity or 0 to infinity, 1 to infinity, 1 to infinity converges, a to infinity समजा, a to, we can write this a to infinity, converges if n greater than 1. Here n is greater than 1, here n is equals to 2, which is greater than 1. So we can say that this integral is convergence, a is greater than 0. So g of x dx, this integral converges, g of x means 1 upon x square, which is less than, see this, e raised to minus x square, which is f of x. So f of x is less than or equals to g of x, because this is f of x, e raised to minus x square is f of x, f of x is less than or equals to g of x, and g of x is a convergence. Then by the comparison test first, this note 3 represent comparison test first, by the comparison test first we can say that, hence therefore by the comparison test first, and f of x is less than or equals to g of x, then by the comparison test first, the given integral from a to infinity f dx, or which is given by integral from, which is that 0 to infinity e raised to minus x square dx converges, and hence we can prove this theorem. Okay, अशा पद्धतीने हा प्रॉब्लेम संपतो. Now we shall discuss the next problem. Second, that is problem number 4. Integral from 1 to infinity log x divided by x square dx. Now we shall discuss this. Let I is equals to integral from minus 1 to infinity log x divided by x square into dx. Let f of x is equals to log x divided by x square. Here the improper integral, and now you tell me, students, at which point this integral is improper. Here the improper integral is diverges at the right end. Improper integral diverges at the right end. See this, it has infinite value. It has an infinite value. So we have to discuss the continuity of the improper integral. आता या improper integral ची आपल्याला value check करायचे. So we shall discuss this. Now we have to check the convergence at infinity. Convergence at infinity. Now we have considered the function f of x. Now we have to consider some particular function g of x, such that we have to consider the function g of x such that x raised to mu. समजा आता इथं जर तुम्ही g of x कन्सिडर केलात, g of x मीन्स x raised to 3/2 घेतलात, x raised to 3/2, तर x raised to 3/2 जर g of x घेतलात, let, because see this, if we consider x raised to 3/2, now we know that let g of, now first of all see this, f of x is equals to log x divided by x square. We can check, we have to consider g of x in such a way that, see here, log x divided by x square, which is approximate equals to root x divided by x square, means is like log x behaves is like root x. लॉग मध्ये निगेटिव्ह संख्या चालत नाही, रूट मध्ये निगेटिव्ह संख्या चालत नाही, सो इट बिहेव्स एज लाइक दिस, सो इट इज इक्वलेंट टू x raised to 1/2 minus 2 means x raised to minus 1/3/2. So we have to consider this as a g of x. We have to consider this as a g of x. So we consider g of x is equals to x raised to minus 3/2. We consider g of x is equals to x raised to minus 3/2. Okay. Now here, see this, if g of x is equals to x raised to minus 3/2, then we have to take the limit. Now limit x tends to infinity f of x divided by g of x, which is equals to limit x tends to infinity f of x means log x divided by x square upon g of x means x raised to minus 3/2. So we can write limit x tends to infinity log x divided by x square into x raised to minus 3/2. So limit x tends to infinity log x divided by x raised to 3/2 minus x square into x raised to minus 3/2 means x raised to 1/2. That means limit x tends to infinity log x divided by root x. Now use the L'Hospital rule, limit x tends to infinity log x चा डेरिव्हेटिव्ह 1/x आणि रूट x चा डेरिव्हेटिव्ह 1/2 root x. So we can write this as a limit x tends to infinity 2 root x divided by x, that can be written as a limit x tends to infinity 2 divided by root x. इथं वाटलं तर इथं लिहा L'Hospital rule, L'Hospital rule. So this tends to, which is equals to infinity, means as x tends to infinity, then 1 upon root x tends to 0. So it goes to 0. So it goes to 0 because as x tends to infinity, then 1 upon x tends to 0, 1 upon root x tends to 0. This goes to 0. आता या लिमिटची व्हॅल्यू 0 झाली आणि लिमिटची जर व्हॅल्यू 0 झाली असेल, then you can use this note number second. g dx कॉन्व्हर्जंट असेल तर f dx सुद्धा काय होतो, कॉन्व्हर्जंट होतो. g जर कॉन्व्हर्जंट असेल तर f सुद्धा काय होतो, कॉन्व्हर्जंट. पण जी कसं आहे पहा, जी कसं आहे पहा, इथं जी ची व्हॅल्यू चेक करा. जी म्हणजेच ॲक्च्युअली कुठं आहे जी इज इक्वल्स टू 1/x². हा, हियर no, so this g is equals to, what is that g is equals to x raised to minus 3/2, x raised to minus 3/2. Here integral from a to infinity g dx, which is equals to integral from a to infinity x raised to minus 3/2 dx, or we can write integral from a to infinity 1/x raised to 3/2 dx. Here n, आता एक theorem आहे पहा, you know that according to this theorem we can write 1/x raised to n greater than 1 असेल तर convergent असतो. So here n is greater than 1, therefore converges. Hence, by the comparison test second, the given integral from a to infinity f dx, which is equals to integral from 1 to infinity log x divided by x square dx converges. अशा पद्धतीनं हे लिमिट कंप्लीट होतं. नीट लक्षात घ्या. सो वी कॅन राईट दिस. ही म्हणजे अप्रॉक्सिमेट व्हॅल्यू एफ ऑफ एक्स लॉग एक्स डिवाइड बाय एक्स स्क्वेअरची घेतलेली अप्रॉक्सिमेट व्हॅल्यू एक्स रेज टू मायनस 3/2. ओके. सो नाउ वी शॅल डिस्कस द नेक्स्ट प्रॉब्लेम. आता त्यानंतर पुढचा प्रॉब्लेम घेऊ. sin square x divided by x square. Problem number 6. Integral from 0 to infinity sin square x divided by x square dx. So let I is equals to integral from 0 to infinity sin square x divided by x square dx. See this. Check this problem. In this case, if we put 0, then sin 0 will be 0. In this case, 0 is not infinity. See this. First, let f of x is equals to sin square x divided by x square. We have limit x tends to 0 sin square x divided by x square, which is equals to limit x tends to 0 sin x divided by x bracket square, which is equals to 1. That means 0 is not a point of infinity. Here 0 is not a point of infinity. Note that, student, 0 is not a point of infinity. So we have to check convergence at infinity. Means we have to check only the right end. We have to check only the right end. Actually, we know that the value of sin square x divided by x square in between 0 and 1 is because sin x, maximum value of sin x is less than or equals to 1, greater than equals to 1. So it is a convergent. The given integral from 0 to 1 is convergent. Now we have to check the 1. Now here I shall write here also we know that how we can check this, multiplying by x square. See this, we know that we have minus 1 is less than or equals to sin x is less than or equals to 1. So 0 is less than or equals to sin square x is less than or equals to 1. 1 square means 1 squaring केलं, by squaring. आता मल्टिप्लाय करा, मल्टिप्लाइंग बाय एक्स स्क्वेअर, देअरफॉर 0 is less than or equals to sin square x is less than or equals to x square, multiplying by x square, because we know that the value of sin x is always greater than or equals to minus 1, less than or equals to plus 1. So dividing by x square, then we get 0 is less than or equals to sin square x divided by x square is less than or equals to 1, means always this value is less than or equals to 0. So now I is equals to integral, we can write this integral 0 to infinity sin square x divided by x square dx in the two form, that is 0 to 1 sin square x divided by x square dx plus 1 to infinity sin square x divided by x square dx. Now from this inequality, see this, from this inequality we can write the first integral is proper. Here the first integral on RHS is proper or convergent, proper or convergent, proper or convergent. That means first integral is proper or convergent. That means we have to use the first integral which is a proper. Hello, मी लेक्चर मध्ये आहे का, कुठं जायचं होतं का, किती वेळात, हां ओके येतो, ओके. Now see this is a proper or convergent. See this integral is a proper or convergent, this first integral. Now we shall check the second integral. Now shall check second integral. See this, first integral is convergent because we have seen 0 is less than or equals to sin square x divided by x less than or equals to 1. हे convergent कशामुळे, we can use this, the theorem, first theorem. What is that first theorem? See this, which is less than or equals to m, integral from a to infinity f dx converges if integral a to x f dx which is less than m. Less than m means this first integral is less than 1. So we can write this second integral. Now integral from 1 to infinity sin square x divided by x square dx. Now we have to check this. हे चेक करत असताना याची व्हॅल्यू आपण अप्रॉक्सिमेट करत असताना here f of x is equals to this, f of x is equals to this sin square x divided by x square. Now if we consider g of x, आता sin square ची व्हॅल्यू लेस दॅन 1 असते. See this, sin square x is less than or equals to 1. So we have to check g of x such that here sin square x upon x square, which is less than or equals to 1 upon x square, because sin square x is less than 1. So we can write 1 upon x square. So we consider this as a g of x. Therefore we consider this g of x is equals to 1 upon x square. प्रत्येक g of x, each and every g of x we have to write in the form of 1 upon x square or k upon x raised to n, because we have to use the useful integral. This is the useful integral. We have seen one important theorem, that is useful integral 1 upon x raised to n. So each g of x we have to consider in the form of 1 upon x square. So now here here sin square x divided by x square, which is less than, here g of x 1 upon x square. So f of x is less than or equals to g of x, which is equals to, we have considered g of x. So we can write now integral from 1 to infinity g of x, which is equals to integral 1 to infinity 1 upon x square dx. Here n is greater than 1. Then by the useful integral is convergent. Is convergent. Is convergent. Therefore, we can write this as, यालाच आपण असं लिहू शकतो की 1 upon x square is convergent. Therefore, by the comparison test first, the given integral by the comparison test first, the given integral काय येतं, is convergent. So given integral from 1 to infinity sin square x divided by x square dx is convergent. And this implies that the total integral from 0 to infinity sin square x divided by x square dx convergent. And hence we can prove. अशा पद्धतीने हा कंप्लीट इथं प्रूफ होतो, संपतो. हा खूप इजी आहे, खूप इजी आहे, याला काही अडचणच नाही आहे. ओके, तर तुम्हाला काही नाही समजलं तर विचारा, काही अडचण आली तर विचारा. आय शॅल सॉल्व दिस अगेन. नाउ वी हॅव टू डिस्कस द नेक्स्ट प्रॉब्लेम. ओके, fifth. Next we shall discuss the next problem. ठीक आहे, तर अशा पद्धतीने हे आपण एव्हरी प्रॉब्लेम सॉल्व करू शकतो, काही अडचण जाणार नाही आहे. सो वी शॅल डिस्कस द नेक्स्ट प्रॉब्लेम. ठीक आहे, बाकीचे आपण प्रॉब्लेम्स आहेत ते आपण उद्याला घेऊ. या ठिकाणी थांबू. काही जरी अडचण आली तर तुम्हाला विचारा. यातले काही प्रॉब्लेम्स राहिलेत ते मी उद्याला घेतो. ठीक आहे. नाऊ वी शॅल स्टॉप हिअर.